So one of our previous lectures, we have seen that how to find the similarity between two distributions. If a distributions are similar or not, we have already seen by simple using the QQ plot. Okay, we have seen this thing, QQ plot, to find the similarity between two distributions. If a distributions X or Y is same or not, find the answer. Now in this video we will try to understand how these things are means in a pre-computer test there have no any computer to plot the graph. So in those days the scientists, the mathematicians are using the KS test to find the similarity between two tests. Let's try to understand how these things are actually work. And the mathematicians, the name of these mathematicians are Kolmogorov and the Smirnov, like that. These two mathematicians are discovered this method. Okay, because of these two mathematicians' name, this name is called the KS test. Now let's try to understand this. Suppose let's take we have two distributions. Suppose let's take we have two distributions x1 and x2, x1 and x2, and on the h distribution, suppose let's take on x1 distributions, we have n number of observations. Suppose let's take on this random variable we have n observed value. So let's take its value is x1, x2, x3, like that, n observed value. And on the x2 random variable we have m observed value. Let's take x, I think it will better I am denoted this symbol here in upper for x1. This point is for x1 and x1, x2, x3, xm, m observed value, and here we will use 2 for x2 random variable. This is the for. So the number of observed value, for x1 is equals to n, and the number of observed value for x2 is equals to m. So now the questions that's come into our mind, the questions that come into our mind is x1 and x2 are come from same distribution. The questions that's come is the distribution of x1. It will be better if we write this. Is this the same? Is this the distribution x1? Is that distributions of x1 same as the distributions of x2? Is two distributions is same? Okay, for this random variable x1 and x2, these distributions are the same. Now suppose let's that examples we have in previous already we have seen. The suppose let's take we have the iris data set, and one parameter of that iris data set. If you remember the iris data set, on that parameter we have four parameter. And on the output of that parameter, and the output of the parameter is class of the iris flower. This is the simple class of the iris flower. There are four parameters: petal length, petal width, sepal length, sepal width. These four parameters we have, and corresponding output we have. These are the iris data set that we have already seen this at the start of this lecture. Okay. Suppose let's take we have considered the petal length, and we will try to find the distributions of this petal length. Okay, so how these things we will find these things already we have seen. The petal lengths are the distributions of the petal lengths are look like this type. It's type of Gaussian distributions. It's look like this type. If you just plot this data, plot the observed value of the petal length, then you will see this kind of, this is actually a discrete set of data. So this kind of discrete plot you will get if you plot the histogram of this data, this kind of plot, this type of, just plot your own yourselves by using some it will be MATLAB or Pythons or R. Use any software, just plot the data of the petal length, then I think you will got such kind of. Now I'm not going to discuss these things, the program part. So just try to just I am going to give the hints of the mathematics behind this thing. Okay, so this is the sample, right? Now the questions is, and how we'll find this is a normal or not? How we will know this the distributions is normal or not? Now let's try to understand in these perspectives, in the perspective of the case test. Simple, the data sets we have first we have to normalize this data set. So in the petal length data sets, do you have first we have to normalize it. First we have to normalize this data. How we will normalize the data? By simple using the formula, means data that we have for petal length minus we have to subtract the mean value of this petal length data, then we have to divide the standard deviation of petal length. The value that we got, that follows the normal 0-1 distribution, means its mean it will be here somewhere here 0, its mean will be somewhere here 0 and standard deviation somewhere. Okay, that's the normalizing thing in one of our previous lectures. Already we have seen. Now let's try to understand through the how we'll find the its distributions through the KS test. Now through the KS test, let's try to find this. I think it will be better if I am going to the Wikipedia, and I'm through Wikipedia. If we discuss these things, I think it will be then better for us. Suppose let's take, this is our data that I have taken, this is our plot that I have taken from the Wikipedia. If you go the Wikipedia and just search KS test, then easily you can find this thing. These pictures I am taken from there. Okay, let's try to understand through these pictures. Okay, so what we have taken here two random variables x1 and x2. For x1s we have the n observations, and for x2 we have m observations. Okay, so now, so suppose let's take the red curve you see in here. This is the sample our x1 curve, and the blue curve that you have x1 curve, this is the sample, this thing simple x1 curve, and the blue curve that you have seen here, this is the simple x2 curve. Okay, now and the x-axis there, it is simple the random variable axis. This is simple the random variable axis, means the observed value of the random variables. These axes are the observed value of the random variables. These axes are the observed value of the random variables. These are the observed value. These axes are, and the y-axis are actually calling the y-axis are the CDF, cumulative distribution functions of these random variables. Okay, that's the two things we have. Now now first, the thing that we have to do, first we have to draw the statistics. First we have to design the statistics. Now the question is how we will design the statistics. Let's see these things. The picture, the black color that you be seen here, the black color that you have seen here, this black color are seen here the maximum distance from these two random variables. This is the CDF, and the black line, the black is the maximum distance that here have for these two random variables. These things are the actually statistics that we have to build. Now let's try to understand how we will write these things to a mathematics. Let's try to understand. So these things actually the maximum distance. Now let's denote this distance through the dnm. This distance, let's denote it. This is the dnm distance. Okay. This is the simple the dnmm distance. This is the simple the dnmm distance. This is the maximum distance among the observed value of the random variables. This value will be simple the supremum value, maximum, supremum or the maximum, or you can call it supremum, or this is the maximum value. Maximum value, okay, from these two value means first the random variable that I have taken here x1. Suppose let's take the CDF for this random variable if x1 is, suppose let's take its f1 and we have corresponding n number of data points. The for x2 let's take its random variable is f2 and corresponding we have here how much m number of data points. So the difference of the CDFs. So first CDF is f1 n minus f2 m. Okay, the differences that we find, and we will find these differences for all points. For all points means for observed value of the x. Suppose let's take its observed value x. For all x's, for all x, we'll find its. First we will calculate the differences for all observed value, and after that we will calculate the maximum of this thing, maximum value of this. So here this thing, the maximum supremum value of this value is called the dnm. These things are actually called the dnm. Okay, I think you will got the answer. We will understand what is actually the dnm. Okay, these f1n and f2m are the simple the CDF means cumulative distribution functions of these two random variable x1 and x2. Okay. Now this dnm, now this dnm are called the test statistics. Test statistic. These dnm are actually called the test statistic for this, for case test. Now how we will use these test statistics to find the to find the these distributions, these random variables are same from the same distributions or not. Now how we will find this thing? Let's see these things. So after that we will assume that our null hypothesis here, we will assume that our null hypothesis is what means they have no differences. So first let's draw the null hypothesis. Null hypothesis is h1 here. There have no differences between x1 and x2. There have no differences. And the alternative hypothesis is here. There have the opposite. There have some differences. Differences between x1 and x2. There have some difference. This is the alternative hypothesis. Okay. Now how we will use this thing? Now simple, we will use this thing means first we have to know how much significant levels means how much confidence we are wanted, we are interested. Suppose let's take we are interested to find the significant level means confidence. Suppose let's take we are interested to find the significant level, or another language we call the confidence, our confidence level, significant level or confidence level. Or confidence. Suppose let's take we are interested to find the confidence level up to alpha. Suppose let's take or alpha. This is our significant or confidence level. Suppose let's take. Now the formula that I have to maintain here. So if we have to decide if our DNM, this DNM, if this DNM is greater than, if this DNM is simple greater than, if this greater than C alpha, into root over of n plus m by nm. If this nm is greater than c alpha divided root over by n plus n by m, if the dnm value is greater than c alpha c alpha square root of n plus m by nmm, if if the finding value of alpha, if this is greater than this value, then we can conclude that we reject the null hypothesis. We reject the null hypothesis. Means it's not. Otherwise, if it is less than equals to, otherwise we will accept null hypothesis, or reject the alternative hypothesis. Which one? Okay, this is the formula. Now the question is, sir, how this formula has come, how these things has come. So this is the simple contributions of these two mathematicians. These things are the simple contributions of these two mathematicians. They have discovered this. If you are interested, then I suggest you please search it on Google. You will find more article on it. Just read this article, then you can easily understand this thing in more detail. So this is not actually our motto to discuss every step in mathematics. Our main motto is to give the intuition behind it, how these things are actually applicable in real world. This is the main intuitions of this lecture. If you are interested, then personally mail me or just read this article through Google. Okay, you can easily find it. It is freely available. Okay, so just now let's try to understand what is C alpha. C alpha. So what is C alpha? Everything is okay, sir. I understand what is DNM, what is this value, M value. Now what is C alpha? Now the C alpha, the common form, the general form, the C alpha. Now the C alpha is here. The value of the C alpha is equals to root of minus half of log to the base e, means natural logarithms, by alpha by 2. So I think you will understand alpha means here the significant or confidence level we are interested in. Generally we are interested to find the significant level at least alpha. If our significant level is greater than alpha, then we will accept the null hypothesis, otherwise it will reject the null hypothesis that we have seen. That's alpha that I am talking about. Here alpha is the level, significant level, or it is the simple confidence level that we are interested. This formula, using this formula, and there are some tables. If you put from this, if you just calculate it using this table, if we calculate it using by this thing, if we put alpha is equals to 0.10, I think it will be better for if you just visualize this thing through a table. Suppose let's take, we have here alpha, and here we have corresponding C of alpha. Okay, if we put the alpha value to 0.10, then from these equations, just using your calculator, then from these equations you will get this value 1.22. If you put this value 0.05, then we will get this value 1.36. Just do these things in your own, then you will easily get this thing. 0.025, if you put it, then you will got 1.48. If you put it 0.01, then you will got, it will be 1.63. We will put it 0.005, means significance level. These things are actual significance level or confidence level. 0.005, it will be 1.73, and if it is 0.001, this will be simple. If you just convert this thing on percentage, So this thing means what? This thing means simple 10%. 10%, okay? This is simple 10%. This thing means simple 5% significant level. This things means simple 2.5% significant level. This means 1% significant level. Like that, like that. These things means 0.5%. 0.5%. These things mean something like that. Just calculated it universal. So this is the sample value of the CL alpha. If this DNM value, if this supremum value, maximum value, if this value is greater than this value, then we only reject the null hypothesis. Otherwise, we will accept it. Otherwise, we will accept null hypothesis. Now, let's try to understand this formula through an example. Then I think it will be better. Let's try to understand these things through an example. Suppose I have taken here two different examples or two different angles to understanding better. Suppose let's take as a first example that I have taken here. So for the A's examples here, I have considering we are interested to find the significant level or confidence level, means alpha value. Or simple confidence that we are interested, means alpha. Suppose let's take we are interested this value is 5%, or in general that in typically that we have taken 0.05 value. Suppose let's take in example 1 we have the n value is, suppose let's take we have our n value is 1000, or the observed value from the experiment x1 that we have. Suppose let's take this the 1000. The m value, the observed value from the random variable x2, suppose let's take this value is suppose 5000. Suppose 5000 this value. Now if you put this thing on this formula, see on this formula, means on this formula, if you put this thing on this formula, then this value will be what? This value will be C of 5, C of 0.05, I think. Alpha is equals to 0.05. 0.05 to root over of 1000 plus formula is what? M plus n by m into n plus 5000 divided by 1000 into 5000. Sure. This value, what is the value of the C is of 0.05? This value, this thing, C of 0.05. So what is 1.36? This value is simply 1.36 into root over of, just calculate it in your own. Then you think you will just write the direct, value, just calculate it using your own. Already I have calculated these things. So now this value will be simply, what? This value will be simply 0.047. This means what? This means if the DNM if this thing DNM value is greater than 0.047, if this value means this value DNM means the supreme maximum distance value, maximum difference value among the observations of the two random variables. Among the observations, the maximum difference value among the observations of the two random variables, if this value is greater than 0.047, okay, if this thing's value is greater than, then we can reject, then that means then we have reject the null hypothesis. Then we reject the null hypothesis, means if the differences, if this value is greater than in 0.047 value, then we don't accept null hypothesis means there have no any differences, means there have no any, means there have some differences. We reject the null hypothesis or accept means accept the alternative hypothesis means there have some differences on these two random variables if this value are happen. Okay, and obviously at 5% significant level, significant at significant level 5%, obviously these things. So if you're interested to find the 5% significance levels, just using this job, just calculate this value, and if you find this value are greater than this value, then you will reject, means alternatively we have accept the alternative hypothesis. That's the job. Suppose let's try to understand these things through another examples. To an example, suppose let's take another example. Example 2. Example 2. Suppose let's take in example 2, we have taken n is equals to some small value. The small value that's I have taken here. Suppose let's take I have taken here n is equals to 30, n is equals to 50, m is equals to 30. Suppose let's take, and the same significance level here also we have interested, means 5% significant level also we have interest, or the alpha is equals to 0.05 we have interested here. Now let's calculate these things. What will be the value? C of alpha root over 50 plus 30 divided by 50 into 30. So this value we have already known. This value is simple. What? This value is simple 1.36. 1.36. What is also here? It is 1.36. That's so. If you just calculate it using your calculator, then you will got this value 0.31. Okay. Now this means what? This means what? If you got this value, this means if the maximum difference of the maximum distance between the observed value of the two random variables dnm, if these things is greater than 0.31, then if this happen, then we reject the null hypothesis at 5% significant level. At 5% significant, that means that means this. So just see this thing. If simple changing the sample size, so just see this thing. If you just simple change the sample size, the value, the difference value are much smaller. Means if you just decrease the sample size, then the difference value will be larger. So from these examples we can conclude that if we increase the value of, if we sample size, if we increase the sample size, that means the dnm, the value of the differences, means the differences, the maximum differences of the observations of the observed value of, maximum differences of the observed value of x1 and x2 are decreased. This means that this actually talking about these things. Okay, these things, if we increase the sample size, this means the differences have to decrease. Just say these things, how much smaller this value is, how much smaller from this one. This is the 0.31 here, this is the 0.047. That's the conclusion. If you increase the value, so in general, so large samples, the value will be more larger. So, okay, I think you got the idea. from this example how these things are actually workable. Okay. So in generally, the rule of thumb is for taken the larger sample. When you've taken the larger samples, the value dnm will be tends to 0. So as the sample size, so if you just write this thing in limiting concept, suppose let's take the sample size I have taken here. Suppose let's take in this sample size here. Let's write this thing in limit form. So the limit of the dnm when we have taken the sample size tends to infinity, this limiting value now it will be 0. This is the sample. These things are simple in mathematics. By example, in pre-computer days, when we have not sufficient amount of computation power, then on those days the scientists, the engineers are doing this technique to find the hypothesis testings. I mean, this is the simple technique that they are on those the scientists are using. And the main contributions on the main contributions of these two scientists, the means Kolmorov and the Smirnov. So these are these two mathematicians. The contributions is like this formula. This is the main contributions on that. Okay, this is the threshold value they have given us. This is the threshold. So threshold. Suppose let's take AHR. These are the threshold value they had given. This is the main contributions in the science, in the research world. They have given this contribution. If you interested how this formula they have come, just read their research article. Then I think then you will easily understand how these things they have got. They have calculated how these things. Just read their article. It is not so hard to understand. Just read once. I think then easily you will got the answer. How these things they have come. These things. Okay. I think from these case states how these things are actually workable on real data on pre-computer days when we have no sufficient amount of computational power. On those days the scientists are using. I think from these explanations you got some idea. Okay. Although if you have any problem, please recap this video. Please revisit this video again. I think it will give some amount of value of your knowledge. Okay, although if you have any problem, please mail me or comment below. Then I will try to give the explanation more simple as possible as I can. Okay, so we will see in next lecture, next video.